Hi everyone, welcome to today's lecture. We have Kian Paimani here today, who's a core developer at Parity Technologies, and he's one of the few instructors who have been part of all our PBA campus and PBA X Wave. So without wasting any more time, I let Kian take over and introduce himself.
Yeah, thank you for the introduction. As mentioned, I work in Parity Technologies and I'm also part of the Polkadot Fellowship. I'm very grateful that I've been part of all the PBAs so far. I don't think that's a title that I hold exclusively. I think this was brought up in the last PBA. I think a few other instructors have been side by side in all the in-person PBAs, but I'm definitely happy to be one of them. Today's lecture will be about smart contracts, and it would be fairly basic. I'll start from the very beginning, building a mental model about what blockchains are, and then I would describe what role smart contracts would play in this. It's early morning here. I'm drinking my yerba mate as well. To any yerba mate fan out there from Argentina or South America, good morning and hello from my side. Last note, you can find the slide deck for this presentation on my website. So there's a section for all the presentations I do. It's all in Markdown. You can go and see it there as well. All right. I think without further ado, we can get started. So actually, maybe I would need to refresh my web page one last time. Apologies for the little delay. So audience is still seeing my screen. I think I made some last minute changes to my slides. Yes, as usual. All right. So as the introduction, and what I want to start with is not necessarily jumping into smart contracts just yet. It's about, I want to talk about the different mental models that have been used to describe blockchains. And I want to go over 3 of them and tell my opinion, and then we will build the rest of this presentation on top of one particular one. So the first mental model of blockchains is to say it's a database. And this is something that I think is the legacy of Bitcoin and its very limited functionality that we have to this day in our ecosystem. I once tweeted that I think this is like a mental parasite, this way of thinking. I think maybe it was a bit too harsh of a word, but what I meant by it is that thinking that blockchains are only databases is a very limiting way of thinking about them. Because yes, blockchains hold some information in the very same way that Bitcoin held this ledger that you see on the screen, a ledger from user accounts to how much Bitcoin they own. But it can do many more things that we eventually discovered over the years. And this way of thinking to say that blockchain is just a database really doesn't capture that at all. So I really find it to be not a good way of thinking about blockchains. Also a little point here for those who want to study more, this way of thinking, I think is also highly tied to the way that Bitcoin was implemented, which is with a system called UTXO. You see it on the screen and you can research it a bit more on your own. Then came around Ethereum and the yellow paper, which tried to describe Ethereum in a very formal way. And as far as I know, this was one of the first places that, the first times that blockchains were modeled in a completely different way. And I like this model way more because it's more capable of demonstrating what abilities blockchains actually have. And this model is a state machine. So for those of you who have done some kind of like, you likely have had this some course about this maybe in school or university, depending on your background. If not, a state machine is a mathematical model mostly used to describe the early computers and some systems, where we model the system as some states, and there's a transition that moves our state from one to the other. So in the diagram, I have like states representing different block heights, so block n plus 1, n plus 2. And a transition takes us from one state of the world to the next. And this transition actually happens to be the announcement of one block. So in the very first state, I have some data associated with it, some state associated with it, where I have like on the very left side Kian having 8 Bitcoin, Nikos having 3 Bitcoin. And then a block comes in. This is our transition, a little bit to the right. Unfortunately, I can have my cursor on the screen. Maybe, let me see if I can adjust this and do it. Yeah, my cursor is there. Okay, that's helpful. I'm going to continue doing that. A transition comes in, and this happens to be exactly what we call a block in a blockchain. So a block of information that tells our system, hey, mutate yourself, update yourself, and change your state. And this brings us to the state associated with block n+1, in which the balance of Kian and Nikos has changed, but more data has also become apparent in our state. So more data was added to this blockchain. And this sequence continues, and this is how the state machine is used to represent blockchains. The terminology associated with this, to recap it a little bit, in the state machine model, we call what we used to call our ledger in this old database Bitcoin model. We usually called it the state. And it's usually just represented as a key to some value. So the key is the identifier of the value, and the value is whatever is stored there. The key could be something that identifies my balance, how much Ethereum I own, and the value is the amount of Ether. And then there's this other term that, again, is used after this phase, so after Ethereum and its yellow paper, quite often in the blockchain space, state transition function. This is a keyword used to represent the logic that dictates what happens. If I go to the previous one, it's the logic that represents, okay, I am currently at this state n. Some input comes in this block. What should I do with it? How should I interpret it? What is the logic behind this transition? And this is what we usually call in this state machine model a state transition function. Not particularly relevant to the rest of this presentation. I use a different naming scheme, but good for you to be familiar with. And finally, coming to my favorite model of blockchains is to generalize this even further. I mean, the state machine thing is accurate. I think it represents all the nuances, but it's too much detail. It contains unnecessary information that I think is too much. And if you want to abstract it a step further, I would argue that blockchains are actually just computers. They behave, and we can see them very similar to a normal computer. This is also, I would say, a legacy of Ethereum. I think a lot of the early Ethereum vision statements were around this phrase "world computer," like one computer with high trust assumptions. Well, actually, no, good trust assumptions. Let's say a secure computer for the entire world. Anyone can interact with it, and anyone can verify that it's behaving correctly. And in Polkadot, and more recently in the Jam Gray paper, if you've encountered these keywords, I think in the Polkadot ecosystem, we're also building on top of the same narrative. We believe in the same narrative. We think blockchains are very general and they can do a diverse set of things, and we are building on top of the same narrative. This blockchain computer, what elements does it have? I think it's worth talking about it. So these two guys. A computer generally has two components that are very important. One is some code, some logic that represents what this computer does. This is what in the state machine model was called state transition function. For simplicity, I like to just call it code. It's some logic represented as code that dictates what the blockchain does. And it has some memory, disk, storage, state, whatever you want to call it. This code eventually wants to say, okay, I calculated something. It's some valuable information. Please store it for me. I want to keep this, how much money I have, how much money you have, and so on. And this is the second component, my computer memory. For the rest of this talk, I just use the keywords code and memory for simplicity. And finally, again, I think to have a good abstraction, users generally can interact with this computer. And I talk about this more in the rest of the presentation. All right, so these are the three mental models of sort of this blockchain computer. And let's dig further. So as mentioned, if we model blockchains like just like a normal computer, they have some code and they have some memory. This code represents the logic. The memory stores all the valuable information that I care about. Users can trigger and interact with this code in some way. It depends on the blockchain, what those entry points are. But generally, I should be able to talk to that code and, for example, tell us, hey, I want to transfer some money. Please execute it for me. And yeah, I already mentioned that. So the memory is also where we store all the valuable information that we actually care about. And I don't really cover it in a lot of detail in this talk per se, but just not to forget, what is the point of this computer? I mean, I already have a computer, right? It's the one I'm streaming from. I have a smartphone in my pocket that is also has a very good CPU and hundreds of gigabytes of memory. Like, why did we reinvent this new computer? Because this computer has some very interesting property, which is that anything that it executes, we can be certain with a very high degree that it's doing it correctly. Like if I want to make a transaction with someone, make an interaction with someone that I don't know and they don't trust me and I don't trust them, it's very useful to have this trustworthy computer in the center help us with that interaction. This is why DeFi is such a big thing in the blockchain space. Anyways, not going into too much detail of that for this talk, but not to be forgotten, this computer, this main novelty and property is that it's trustworthy. It's because it's decentralized, because it's using a lot of cryptography and proof of work and proof of stake and this and that under the hood, we can trust that whatever it's executing, it's actually being executed correctly. All right. So now I want to go into sort of the evolution of this blockchain code or the blockchain state machine and see how it actually evolved over time. I would pose as a question, and I'll give you a few seconds to think about it. What is sort of the code and memory of the Bitcoin computer? What does it do? I will continue on that in a second myself. But giving a quick break here. So Bitcoin is, I would describe it in a generation of blockchain computers that had a fixed code. Like it did one thing and there was no way to really extend it. So the main ability of the Bitcoin computer is to transfer Bitcoin. And is it really extensible? Yes and no. For simplicity, I would answer this, is it extensible? Completely no in this lecture. But to be accurate, Bitcoin actually has a very primitive scripting language that allows you to put some custom logic in there if you wish, if you wish so. But compared to what, later on Ethereum allowed or nowadays smart contract platforms allowed or then Polkadot invented, it's like comparing, a bicycle and a car. It's very limited. So for sake of simplicity, I would categorize it as no, it had a fixed code, it did one thing, and it did it just that. So with this definition in mind, I would then pose, gradually going to the smart contract topic, I would define smart contracts as a way to make this blockchain computer programmable in an extensible way, in an actual flexible way that we can do useful things with. So then let's think about Ethereum. So Ethereum is indeed a programmable blockchain. And I'm assuming most of you are familiar with it. So I would tell you step by step what are the things that the Ethereum code allows you to do. So the Ethereum computer, very similar to the Bitcoin one, does allow you to transfer ETH. So the code and the memory has all the logic and all the infrastructure needed to handle this, everything that Bitcoin also already did. But there is also a part of the Ethereum code, the Ethereum logic, that says, hey, someone can come to me and upload a new contract, upload a piece of code that I then store in myself. And later on, I would allow people to interact with it. So then another functionality of the Ethereum computer would be that it would allow you to come and interact with not, Ethereum itself, but something that was uploaded to it, a piece of contract, a piece of code that was given to it. And again, not to forget the whole purpose of this. What's the main sort of magic behind this? Why is this valuable? Because in the very same way that we trust the Bitcoin computer to execute the transfer logic of the logic of a of a BTC transfer, and in the same way that we trust the Ethereum computer to correctly execute the transfer of some ETH tokens, we can also be sure that whatever was this contract code, it was executed correctly. So that's that trust and trustworthiness property of the blockchain itself is something that all the smart contracts that are hosted in that blockchain also inherited. And that's why we managed to build a lot of interesting applications with smart contracts and blockchains. Okay, so with all that in mind, and with all my abstract and somewhat philosophical descriptions of what is a blockchain and so on, I can give you now finally a definition of what is a smart contract. Smart contract is a way to make both this code and memory component of a blockchain computer extensible, add some logic to it, extend it, and retain the same security guarantees that this blockchain system was originally giving to us. All right, I think I'll go a bit further and then I'll do a quick break for questions. So let's look at the components or the anatomy of smart contracts, going into a little bit more detail. So as stated, a smart contract also has some code because it has to represent some logic, and it can have some state or memory. So that code can, say, hey, I did some computation, please store it now for me. Or I realized, some DEX swap happened, someone exchanged Ether for USDT, please reflect this in your memory for me. And there's an interesting opinionation, I would say, from the Ethereum world. A quick apologies, I'm using the word EVM here, but I haven't really described it yet. It would come in an upcoming slide. You can replace it with Ethereum. In the Ethereum world, there's an interesting opinion that I would call it an implementation detail, but it's something that everyone had to deal with later on, that they said, okay, we have this account and the accounts can own some Ether. It would make things a lot easier if we just say, hey, any contract that's uploaded to the blockchain as well is very similar to an account. So it inherits two properties that all the accounts have. It has some address, which is how we can identify that contract. And in the very same way that an account can own some Ether, can own some money, the contract can also do that, because the contract has an address, and if you have some money associated with it, some Ether associated with it, this money is now owned by the contract. So contracts are kind of like accounts that are smart, and they can autonomously do stuff. And this opened a lot of doors, again, for interesting applications where you can, for example, deposit some money in the contract. This wouldn't have been possible without this implementation detail, I would say. Interestingly, it also opened the door for a lot of sort of attacks and hacks and stuff, which I will cover a little bit more in the rest of this presentation. All right, this EVM and so on, I used a lot of keywords so far that now I would describe all of them. So in the Ethereum world, which is also sort of the main domain of smart contracts that is dominant today, and I want to cover it. The primary language used to write these smart contracts is called Solidity. This is a language that was invented next to Ethereum. There's a lot of alternatives out there, but languages are pretty sticky. It's I sometimes say Solidity is like the JavaScript of the web. In the same way that everyone likes to criticize JavaScript, it has this flaw, it has that flaw, so on. Because being the first mover, it's still around. And people have built transpilers on top of it, like TypeScript and so on, but the language is too sticky to want to ever go around. I think Solidity in some sense is is in the similar category. The component that can execute Solidity with a compilation step in the middle is called EVM, and this stands for Ethereum Virtual Machine. So this is like a virtual machine that can ingest compiled Solidity code and execute it. So this EVM is one of the things that is part of the Ethereum state transition function. Like Ethereum's code contains the EVM. And the compiler that actually compiles Solidity to EVM bytecode is very unimaginatively called SolC, Solidity compiler. So these are just some keywords related to contracts in Ethereum. All right. Next, I want to introduce you to a few important components of contracts, or things that as users of contracts or developers of contract, we have to deal with, most notably this notion of gas. And I want to introduce it through a question. So let's say a contract has been uploaded to Ethereum, and I come and say, hello, Ethereum, please, I want to interact with this contract of yours. Here's some input. Please call this function in this contract for me, which supposedly does something. How can Ethereum know that? What we have to remember here is that Ethereum as the platform has no clue what is this contract doing. Is it gonna execute in 1 millisecond, 10 millisecond? Is it gonna go on an infinite loop? Is it gonna bloat my state with a million storage items or something? Ethereum has no idea what this contract is supposed to do and how much resources it's meant to consume. This is a very common problem in blockchain systems, mainly when we're dealing with this phrase untrusted code. Some code that I don't know who wrote it. I don't know if they were malicious, benevolent, or what. And this is why it's very important for smart contract platforms to first of all have to be able to have a deterministic cost for the execution of these smart contracts. And this is where this notion of gas comes in. So it has two components. One is that as Ethereum is running a contract, this EVM guy is kind of keeping a counter of, okay, how much work have I done? How much work have I done? How much? And they call this gas. Again, it's just like a counter saying, hey, I have burned this much CPU power and this much storage resources so far in executing this thing. And this process is called metering, usually. And this is also why every time you invoke a contract, if you ever send any contract via MetaMask or something, you might see this option, hey, do you want to specify your gas limit, or do you want me to guess it for you, or put some default there for you? This gas limit is something that whoever invokes the contract is telling to Ethereum as a upper bound guarantee, hey, please execute this contract for me, and I promise you it won't consume more gas than what I'm saying here. And if it does, because Ethereum is also metering the execution, if we actually reach that gas limit and the thing is not over, Ethereum says, okay, you're done. You paid some fees and your operation is also not over. I'm sorry, but you violated the rules here. So this is where this metering and gas limit comes into play. Another aspect that is also relevant for contracts, but frankly, it's also relevant for all blockchains, is that this execution, whatever this contract is doing, has to be completely deterministic in its output. What I mean by that is that if one validator in some blockchain network or one node executes this contract, another node executes it a minute later or a week later or a year later, they must all come to the same conclusion. They must all come to the same output. And this is achieved through two means. One is that, well, some languages or some virtual machines are deterministic and some are not. Ethereum EVM is obviously a deterministic virtual machine in that, generally speaking, all the operations that it can do are deterministic. There's no sort of random behavior in it. And I think it's also a good time to remind everyone this problem that I described is fundamentally why we cannot do undeterministic things in blockchains or in smart contracts. You cannot make an HTTP request and say, what's the weather in Lisbon right now, and put that on a blockchain, because this weather changes throughout the time. So if I'm executing this now and another node in the network is syncing the blockchain a week later, the weather is going to be obviously different. So even beyond that, there's no guarantee that this HTTP endpoint that returns the weather would actually, return the same thing even at the same time. So anyways, undeterministic things, no go in all the blockchains and in smart contracts. This gas situation also applies to how much memory a contract consumes. I don't go into as much detail of it here, but just for you to be familiar with it, is that it's also a overhead for Ethereum to store all the state and memory associated with all these contracts, and this is something that it needs to take into account. So it's a mixture of a couple of approaches, and I think these things have changed over time. Like how we deal with this problem has changed a bit over time, but it's fundamentally the same problem. So sometimes you kind of pay for your storage usage as part of the gas. Some systems opt for like a deposit system. So they allow you to store as much data as you wish on a blockchain, but they say, look, for every byte of deposit, for every byte of storage that you want to store, put a tiny cent. Give me a tiny cent, and when you free the memory, I give you your cent back. This is both the deposit and the state rent model is more or less like this. Yeah, more to be said on this, but I think it's a fairly advanced topic. I just want you to be aware that, in the very same way that the execution time, which was this gas story, is a problem for Ethereum with regards to contracts, because they are untrusted code, and we don't know how much CPU they're going to use. We also don't know how much memory they're going to consume, and this has to be taken into account. All right, bringing it all together, I have a very artistic visualization of the life cycle of a contract and what happens. So quickly going over it, you start on the left side. So a contract is written by some developer. This is in a .sol file, so it's like a Solidity. What you would do is that you would give this to your Solidity compiler, and this compiler would compile this code for you and give you two outputs. One of them is something that we are familiar with, is like the binary bytecode. This is what the EVM can execute, and eventually this bytecode, this is like binary machine code, is uploaded to Ethereum via a contract, and then Ethereum says, okay, this contract is now part of me, and a user can later come and interact with it as it's happening in here. Something that I haven't covered here, and I'll briefly talk about it, is that the Solidity compiler actually happens to give us another file as well. Questionable name in my opinion, but it's called the ABI. It stands for Application Binary Interface. I say questionable because I think Application Binary Interface is a bit convoluted in what it said, in what it does. The purpose of this file is as follows: is that this user who wants to interact now with my blue contract, which I just compiled, generally would have no information to know, okay, what is even this contract? What is the entry point? Okay, the contract is like a vault. Okay, I can deposit some money into it. What is the parameters of the deposit function that my wallet needs to trigger? There's all this information about like how to interact with the contract. What are the entry points? What are the characteristics of it that a user and their wallet and their application needs to know about? And this is all the information that this API file is providing and fixing for us. These files are usually like completely kept, like they are kept off chain, as in they're not like really uploaded to the blockchain. There are services that allow you to like upload your contract and the API file, and they're verified for you, and then the wallets would connect to it and kind of have some also have some like security guarantees that, okay, this API file is not lying to me, it's actually correct. And then this allows wallets to know what these contracts are, what are the entry points, and how to interact with them. Well, I'm not sure if it's a better word, but in the Polkadot world, we call this, what is the analogous of this file, the metadata. So it's like some meta information about some opaque binary file that allows us to interact with it. All right, so next I have like 2 case studies to talk about, like just like simple contracts to write. But I think this is a good time to have a few questions. So let's do that.
Yes. Thank you for great insights on your blockchain definitions. So we have one question. They're asking, we often refer to Ethereum being a complete Turing machine. Is it the same thing that you explained with Ethereum being a state machine?
Actually, yeah, I mean, I don't have them like fresh in my mind, but the definition of Turing completeness, I do remember it was introduced to me in the same course in university where state machines were. So the topics are definitely connected. But I think for the exact answer in that, probably Wikipedia can answer it better than me trying right now. So I would defer that. As for Ethereum being Turing complete, yeah, it's a correct statement in that the contracts in Ethereum are like the Solidity language is Turing complete, although definitions sometimes differ a little bit. But if you accept that, okay, the contract has this gas limit, and also there is always this limitation that you cannot upload a long-running application as a contract to any blockchain, because there's always this, like, a block comes, we execute some stuff, then we forget about it until the next block, and then so there's always this like disjointness in it. But if you exclude this flaw, yeah, then it's Turing complete.
Thank you. Next question is, what are the limitations for allocating memory? Is it persistent?
Yes, in fact, that's a good point. So one thing I don't like about my blockchain model is that maybe I should use disk instead of memory, because the type of storage that we have in blockchains is always persistent. Like there is in fact no impersistent memory because of this disjointness that I just talked about. Because whatever you have in your transient memory goes away once the block execution is over. So whatever you store in your blockchain state or storage in general is completely persistent. And I think this is a little bit misleading in this computer model that I say, because I use the word memory to represent a persistent. Yeah, maybe I should emphasize it's a persistent memory. Whereas in most computers, memory, or what we call RAM, is actually more transient memory. Going back to the answer, yes, it's persistent.
Okay. One more question. Is calculating gas the same than calculating weight on Polkadot site?
Yeah, there are similar concepts here. There are nuanced differences between the two, but it's a very similar concept, yes.
Thank you. That's it for now. These are the
All right,
questions
thank you for the questions. I will have a similar one again a little bit further in the presentation. All right, so let's talk about like a few sort of like contract one-on-one ideas that have been, I think, used out there a lot in tutorials and stuff. And also use them as like just case studies of what can be built on a contract. I think one of the simplest one is like an escrow contract. So the scenario is as follows. There's a buyer and a seller, and they want to do an exchange in the real world. One person wants to sell a car, the other person has Ethereum, and they want to buy the car with Ethereum. The problem that this contract can potentially solve is that the seller might be spammed by people who don't even have the money to buy it. So someone comes and wastes the seller's time by saying, "Hey, I want to buy your car. Like, what's the model? What's the engine? The audio system, blah blah blah," and then they just piss off and the thing ends. So the escrow contract would allow someone to come and lock an amount of ether that is equivalent to the value of that car in a contract and say, "Look, see, I actually have the money to buy your thing." And you can verify that it's there, and the seller can indeed do that. And then they can proceed to sort of meeting in the real world, and if they sort of agree and their vibes check and so on, they both have to approve they both have to go to the contract and say that yes, we met in person, and the exchange is going to happen, and then the contract would release the funds to the seller's account instead of the buyer. So the buyer puts the money in, then it goes to the seller's account if both approve. And if both don't approve within some timeout period, the contract can say, hey, I think something is wrong, hold revert everything. So send the money back and nothing happens. It's an interesting use case because it does solve this spam problem. Like you can use blockchain and its publicity and its trustworthiness to demonstrate that you have the means to purchase something. I think it's also worth noting that it doesn't solve the problem of if the buyer and seller meet in the real world and the seller has brought a couple of their friend, and they coerce the buyer to click the button and say approve and so on. It doesn't really solve those problems. Like blockchain has no way to know if the exchange actually happened in the real world. It can just rely on the both parties sending a approved transaction. But there is a niche legit use case that is being solved here, and I think it's a very simple contract that anyone can go and actually build. I think this escrow contract, again, is one of the most common tutorial contracts I've seen out there. This one I've seen yet less. It came up within the last year in some random conversations I had with friends. I tried to Google it and find it. Maybe I'm not Googling the right word or searching for the right word. Because I think someone has built this, but I couldn't actually find it. So, if you find it, let me know, or go build it. I think it's a cool idea. So I call this Web3 roulette. It's a very stupid game. It has no, I'll just tell you in advance. It's not nearly as useful as the previous one. It's completely a gambling machine where this roulette game, with the pistol and stuff, how that works. So everyone sort of joins a game and they bring some money. They say, hey, I want to join in your gambling game. Here's $10 from my side, $100 from the next guy, and so on. And at some point, this game says, okay, everyone who could join the game is over. The joining phase is over. And then the contract would have to utilize some randomness, hopefully a good source of randomness, and name one of the participants as the loser. And then the loser gets nothing back, and all the other participants receive a share of that loser's initial deposit. Again, completely a sort of gambling too, but I think it's again an interesting. It could be an interesting way to learn contracts and do some coding on them, and I think similar to the escrow one. You could argue it's for people who want to play the stupid game, it is a good way to do it. You don't need to have one person to whom you give all the monies and you have to trust that this one person to not screw everyone. The logic of the game can be entirely encoded as a smart contract, and it could work well. All right, these are my two sort of case studies of what contracts could do. Let's go into a couple of more advanced topics. So first, I want to talk about this keyword called composability, which we hear a lot in blockchain world. It's a little bit abstract for those who are maybe less familiar, but to be fair, this is not one of those areas where in the blockchain world we have invented our own keywords. Composability is indeed used in software engineering a lot. When you have in the classic, for example, object-oriented programming, when you have two objects and they want to talk to each other and mix their behaviors and create something new out of their coordination, we call that composability. And it's exactly the same thing here as well. Composability refers to the fact that these contracts could, call into one another and mix their functionality such that, something emergent and new comes out of it. And how this happens, I think, goes back to this analogy that I have in my slide here. So for anyone who has purchased the VPS, you're familiar with this, with what's happening here in this VPS model. There is a server in the basement of this VPS provider, Hetzner, I don't know, Amazon, whatever. And this server is one machine, but there are a number of virtual machines that are built on top of it. So when you purchase a VPS, you're logging into your VPS and you SSH and go into it, you feel like this is a computer with hardware all given to you. But in fact, it's virtualized. Like it's not really a computer. You and probably hundreds of other customers are all sharing the same computer, and you all get this feeling that you're the only resident, but in fact you're not. And Ethereum and contracts is very much the same thing. Ethereum is like the hardware, is like the provider, and these contracts are like little VMs that live in this shared environment. And why is this related to this composability topic? Because this composability is only possible, at least in an easy way, because we're in the shared environment. Because there is one hardware, there's one Ethereum, and there's two contracts that both live on Ethereum. This allows these two contracts to then easily talk to one another. If they want to call a function, one wants to call a function of the other one, this is just a normal function call. And immediately the answer would come back. If the function succeeds, it returns, hey, I succeeded. If it fails, it returns some error. And finally, I want to use this as an opportunity to also describe these extension of this composability that we hear a lot in the blockchain space, synchronous and asynchronous composability. Again, mouth-worthy, like a mouthful keywords, but again, I think the keywords are used in computer engineering as well. So synchronous composability is what I just described. Synchronous generally means, it's like bam, bam, like you call it, comes back. It's like synchronous, right at that time you get an answer. If a contract wants to call a neighboring contract, it's like a function call, the answer comes immediately, I can continue my work. Asynchronous composability is what we see in the modern days with like the Ethereum and rollup model, or like the Polkadot and Parachain model, where you have two completely different blockchains. And there's a contract in one, and there's a contract in another one. And these two poor guys want to talk to one another. And this is where we call it asynchronous composability, because then the interaction is no longer immediate. Like one contract says, hey, I want to call a function in the other contract. And they dispatch this message, but they cannot really wait for the answer because they don't really know when the answer would come, if at all. And it's asynchronous composability is generally quite painful to program. It's very error prone. It's terrible user experience because things take a lot of time. It's slower, but it's a trade-off that we have accepted. Well, not we, as a part of the blockchain ecosystem generally has accepted in order to gain more throughput. I'll talk more about this as an open question at the end of the presentation. Generally speaking, the reason we have asynchronous composability in some places is that because we realized, okay, if we split our one blockchain into like many blockchains, we can have more throughput. But the cost of that is that now some communication is asynchronous. All right, so this was like a brief intro in composability, which again is just a fancy way to say contracts can call each other and talk to one another, and how it's similar to this like VM and VPS provider situation, and what synchronous and asynchronous composability means. And then I want to talk about actually a very popular sort of attack that can happen because synchronous composability is possible. So this attack is called re-entrancy attack. I think some of you, I would imagine a lot of people have heard this name. And I want to actually go over it here in detail. So for those who are familiar, sorry, this is going to be repetitive. But if not, I would like to actually finally, it wouldn't be a presentation without some code, right? So finally show you a bit of code that is vulnerable to this re-entrancy attack. So I would pause here and give you some time to read this on your own. This is a very dumb contract that allows two very simple things. It's like a bank. You can go and deposit some money into it, and later on you're supposed to be able to withdraw your own money from it. And imagine while you are depositing, like while you have some money in this Ether store bank contract, maybe it gives you some perk. It grants you some revenue. It might give you an NFT, whatever. So I will pause here for a minute for you to read this code. In the meantime, I would like to ask the organizers if we have a hard stop in 13 minutes, or because if so, I think I should speed up a little bit. Or is it okay if our Q&A at the end goes a bit over?
It's okay. We can go a bit over.
Okay.
We
Okay.
don't
I
have a
mean, I
hard
think I
stop.
will be over by at the hour mark latest, and then we can
Yeah,
have like 5-10 minutes questions at the end.
sure.
All right, so let's go over this. So this contract, I will walk over the components little by little. It has like, so this is all Solidity syntax, by the way, but you can imagine it's pseudocode or don't need to understand all of it. It's declaring that, okay, I store some memory, in fact, with my analogy, or some state component that is a mapping from address to a 256-bit number. And this is like, there's people that come and deposit money into my contract. I need to keep track of them. All good. Then there's a
Sorry,
deposit function.
one interruption. Could you please zoom in the code a bit?
It's too small.
Yes.
Let me, oh yeah, that's true. Better now? Yes. There's a deposit function, which basically says, whoever is the sender of this message, whatever value was in that message, please store it in my mapping, in this balances mapping that I described above. And then there's a withdraw function that, again, makes a lot of sense. It first checks that whoever is the sender of this withdraw message, do they actually have some balance deposited with me before? And then make sure this balance is more than 0. So if you haven't deposited anything, goodbye. Just kick them out right now. Don't waste my time. You haven't deposited anything, so you're not eligible for any withdrawal. Then we have this like a little bit of like quirky syntax, which is Solidity's way of saying, whoever was the sender of this message, please send back whatever whatever balance they had in my contract. So whatever I retrieved in the previous step, send it back to them. Which again makes perfect sense. I think in a normal programming paradigm, this would have been a very acceptable code. And then we're finally saying, okay, we have sent them their money back. Please send their money to 0. So whatever is the new deposit value of this sender is now 0. So they're basically reset. This logic would be completely correct if we didn't have the situation, like this logic is correct if we assume users interact with it, so humans interact with it. But as I said earlier, EVM has this assumption that a contract is indistinguishable from a user account. So instead of you going and interacting with this contract, like click by click with your wallet and MetaMask, you can actually deploy another contract that deposits and withdraws. So another contract, through composability, in fact, synchronous composability, can communicate with this contract. And then what could go wrong if that is the case? Because the other contract that is calling, that is sort of the recipient of this message, can declare what to do upon receiving that message. So imagine when we send this balance to the recipient, upon receiving this balance, would say, okay, I received it. Now I call withdraw again. So while we haven't even reached this line of code, we sort of, and before we even had an opportunity to set this balance back to 0, another sort of in another thread, in another execution, we come back here because the recipient called us again. Maybe to elaborate on it a bit more, in this case, the attacker contract would look something like this, as simple as this. I mean, I've simplified it a little bit, but this is like the function that is sort of the entry point where we receive our money back. And upon receiving, we just say, hey, go back to the Ether store and call withdraw again. And the EVM would exactly follow that code path, which means before EVM in the previous call had a chance to realize, hey, I already withdraw, it would say, oh, okay, this person wants to withdraw again. What happens under the hood is that you start with withdrawing other people's money, actually. All right, I think this is the best I could do, with some snippets and without showing you a demo with very simple snippets of how this attack would work. But generally speaking, this attack is called re-entrancy attack. Some function in EVM is executed, and at some point it communicates with another contract or account or contract. Again, they're the same things. And this recipient would force us to start over again before we had the chance to finish the effects of the current execution. This is why in a lot of like Solidity best practices, they say stick to this paradigm. Check if the operation should happen. Apply all the effects. Like, if someone's balance is going to be 0 after this interaction, set it as soon as possible to 0. And only then interact with other contracts and accounts. Again, because they can force you to re-enter your own code. I think billions have been stolen with this bug, literally. All right. That's more or less the end of the... Oh, wow. I think I need to zoom out a bunch. What is going on? Okay. That's the end of like sort of the general smart contract lecture. I will use the last 5-10 minutes to tell you a little bit about the state of smart contracts in Polkadot, and then we go for Q&A. So first, what is Polkadot? Polkadot is a sort of like a very general computer. I would say a decent step more general than Ethereum, which doesn't allow whose code doesn't allow other smart contracts to be executed within it, but rather other blockchains to be executed sort of within it. Polkadot is a blockchain that secures other blockchains. That's kind of its original value proposition, at least. This is the original Polkadot from years ago. Evolving, but I think we can stick to that definition for now. And a little detail I want to add here is that because Polkadot was this like slightly more infrastructure level project, it always assumed that, okay, my role is like to secure other blockchains. I don't really need to like provide smart contract functionality myself. I'm going to secure other blockchains, and they do go and provide smart contract functionality. And this is indeed something that we have seen happen in the ecosystem. There is, I think, maybe like dozens of Polkadot-based blockchains that use the technology stack that Polkadot's team has created over the years to host different sets of smart contracts. And indeed, we have actually not limited ourselves to Solidity and EVM. So what you see on the right-hand side here, supposedly this is the logo for Solidity. I also found it just yesterday. Polkadot-based blockchains have all the components and modules and necessary tools in order to support both Solidity to EVM contracts. And we have also innovated a bit and created a completely different language, which is based on Rust. It's called Ink. To write your contracts in Rust, it's called Ink, and then execute them not on EVM, but in the WebAssembly virtual machine, WASM. There's a very cool website for Ink. You can link to it here. It has fantastic, documentation and showcases and a very nice list of all the projects that use either of these two tech stacks, and there's abundant number of them out there. That being said, things are also changing a little bit. So one sort of like wish for change in the Polkadot community has been that it would be nice if not just, teams building on top of Polkadot provide smart contract functionality. It would be good if Polkadot itself would also provide that. So there would be a smart contract platform somewhere where, it's labeled as Polkadot smart contract, not, Moonbeam or Akala or Astar, like not like a third-party blockchain secured by Polkadot, but Polkadot itself. And while doing so, also the engineering teams and some of the good thinkers and sort of rockstar engineers of Polkadot have also started to experiment in the meantime with a new virtual machine, which is based on RISC-V, which actually has happened to be a very hot topic these days. I think there was a blog post from Vitalik from 2 days ago suggesting a similar approach for Ethereum rollups. Anyways, long story short, we have also in the meantime explored new virtual machines, and RISC-V happened to be like one of the most sort of promising ones. And we have built a new smart contract VM based on RISC-V, which we call PokaVM, which can And the nice thing about it is that because RISC-V is very popular, not like EVM, which is like something very niche and specific, you can compile a number of different languages to this Poco VM, including Solidity. But we also have examples of contracts being written in pure Rust, so almost Rust with no modification. I have the SUI logo there because there was no logo for the Move language, but there's this programming language first invented by Facebook, I believe, called Move, and nowadays adopted quite heavily by SUI and their other fork, I forgot their name, Aptos. We also have plans to, for example, write sort of the necessary components to be able to compile Move contracts into PocoVM. And again, the difference sort of here is that Polkadot is aiming to provide smart contract functionality for the first time under the Polkadot brand, under the Polkadot umbrella, and not like a blockchain secured by Polkadot. So this is something that is work in progress. I think a big part of the workforce of Polkadot is working on it as we speak. There's a demo website that you can see the link to here. Some preliminary documentation about how the system is going to work, and there's a deployment of it available on one of our test networks, but it's something that would come live to Polkadot in H2 2025, so the second half of the year in which we are right now. All right, last note, I want to just pose this as an open question. I will give you some comments from my side about it, but it's food for thought for you to take later. We talked about this composability, synchronous versus asynchronous. And I already elaborated on it a little bit at that time so what happened in the blockchain space was that we built blockchains. There were these computers and they were extremely slow. And one way to make them go faster is that you create different sort of shards of it, different copies of it. It's not even necessary to call it shards, because you can have like just the realization is that, okay, if we have more blockchains, we have more throughput. And this led overall to this multi-chain paradigm. And I think 3 sort of ecosystems have seriously explored this. Polkadot and Cosmos started from many years ago, so starting from 2017-18, with some subtle differences. They were both multi-chain frameworks, Polkadot and Cosmos. And gradually from 2021, Ethereum converged to the same idea through this roll-up analogy. So what Ethereum calls roll-ups is very similar to what Polkadot calls parachains, very similar to what Cosmos called, I don't know, something, but they're all the same thing in some sense. They are creating more copies of our blockchain computer so we can have more throughput, we can have more processing power, we can have more data stored. But the cost of this is that it's this asynchronous composability problem, among a few other flaws. The cost of it is that, and I think it's really like still for me an open question of like whether this direction of like multi-chain is like really the holy grail, or is like a short-term compromise that we're going to regret in some years. To be seen, I would say, and I want to leave it for you as well for some food for thought. Generally speaking, I'm using the word app chain here. Maybe I should have actually used a different word. Multi-chain is what I'm talking about. The app chain sort of thesis is that, we should have many, many blockchains, and one app should go in one chain. So it's like one chain that does only the logic related to one application. But what I mean by it here is simply multi-chain model. Maybe last comment on it is that I think it's interesting to observe that, for example, Solana is betting on the opposite side of this, as in, we don't need multiple blockchains. It's good to build just one blockchain that is extremely fast, and that's gonna like solve all of our problems. Again, to be seen where this ecosystem would converge at the end. I think it's probably going to be somewhere in the middle, as in like, end of the day, we need some degree of horizontal scaling versus vertical scaling. So what Solana is doing is vertical scaling. We have one system, we keep one system, and we just make it beefier. So it's like vertically goes up. Horizontal scaling is having multiple blockchains. I think we need to settle somewhere in between the two. All right. A recap of conclusions. So smart contracts are basic ways to build more applications on top of the baseline blockchain computer. It's a way to extend it. It's a way for you to upload your program into the blockchain computer, and the blockchain computer would simply run it for you. And generally speaking, it's a very sort of like battle-tested way. It's been around for more than a decade now, or I think almost around a decade. I mean, Ethereum was sort of invented in 2014, 15, and I think it launched in 2015. We're in 2025. So, people have tried it for a decade. I think generally speaking, it's very advisable to say if you have an idea that you think can be implemented in a blockchain-based system, and you have some doubts whether, I should go build my own rollup with OP Stack, I should go build my own parachain with Polkadot SDK, I should go build my, I don't know, this and that. One of your options is also just to try and see, hey, can I just implement this as a smart contract? And I think that's very advisable to say, exactly because of the second point. Smart contracts are a very, battle-tested way. There's a lot of resources on it out there. It's fairly cheap to deploy anything as a contract. So if you're if you're dipping into the blockchain space as a developer, as a builder, as a founder, just now, or you're early in your journey, I think starting with smart contracts for any idea you have is advisable. All right, that's it. Let's go to the second round of questions, or maybe third.
Okay, sure. So the question asked is, if all chains can interact with one another thanks to Polkadot, what's the point of smart contracts then? Why not just have one blockchain, one app?
Yeah, so we can, and that's something that Polkadot did bet on heavily at the beginning. And I think it's still part of our opinion on the future. Yet its downside, yes, so the downside of that is that then all of these apps can only compose asynchronously because they are each in a different blockchain. And these blockchains, have different block times. One of them could be offline for a minute. One of them might be busy for a minute and doesn't have time to respond to you. There's like a lot of complications that come with asynchronous composability at the developer experience level, at the user experience level, and that's the cost of it. That's the downside of it, I would say. Whereas, if these two apps that we're hypothetically talking about here were in the same shared smart contract environment, they could communicate and compose with one another much simpler.
Okay, just going back when you explained about the Ethereum being deterministic, somebody asked, how is an NFT token ID generated randomly since all things in Ethereum are deterministic?
Yeah. This is one of those areas where I think cryptographers have saved the day with blockchain space. So indeed, we cannot have really random, like within our computers. If I ask, if I go to some programming language and ask for randomness, what it does is either it gives me like some pseudo random stuff, or it actually uses some real world sensor, like temperature, or like something that is like actually a bit random, and mixes that. Utilizes that as a seed for my randomness, which we obviously cannot do in blockchains. But there are, again, beyond my understanding, but I don't know how it works. I know what it does is that there are verifiable random number generators through cryptography. And blockchains generally use that. And this is actually one of the services that a lot of a good smart contract platform should provide to its residents. In the very same way that an operating system gives you some APIs. If you want to write to the file system, here's an API for you. Good blockchains all have secure sources of randomness that is deterministic, but known to be unbiasable. And by unbiasable, like unpredictable and unbiasable. So no one can kind of tweak this randomness to go in certain direction, and no one can also predict it. But it's still deterministic. Everyone flips the same coin, everyone gets the same outcome, but yeah. I think that whoever asked the question, they can look a little bit into the topic of VRFs, verifiable random functions.
Thank you. And when you were telling about re-entrancy attack, there was a question related to that this re-entrancy attack should happen in MS right? Since code is simple and should be executed each line fast. Or there'll be another bug exploit this. I think I have to ask him to rewrite this question
No,
because
I think I got it. By
if you
MS,
can understand. Okay,
I think they mean like in a millisecond, like in a snap.
okay,
Since the code is
sure.
simple and it should be executed each line fast, or there will be any other bugs exploit this. So I mean, I got one part of the question. I can elaborate on it. In that, like, how fast this code runs is a bit irrelevant to the fact. Like, end of the day, we are in the world of computers where everything is actually sequential. There is no well, EVM is a sequential virtual machine. And before multi-core CPUs, when you had two applications open on your computer, there is no parallelism going on. It's your CPU end of the day is executing one instruction at a time. It's doing it so fast that you have the illusion that things are happening in parallel. So let's first start by asserting that this code, no matter if this operation is fast or slow, it happens in a single thread. And EVM is absolutely single-threaded as well. So no matter how fast they run, the problem is that you call this function, and you think you're going to continue with this, but the recipient of this function actually forced you to come back here before you had the chance to finish this last bit. So time is not relevant. It's the order that matters, order of instructions.
Okay, thank you. One question is Polka VM a prerequisite for Jam?
Yeah, okay. I mean, we didn't really talk about Jam and Polka VM in detail here. Let me use this as an opportunity to tell what even Jam is. So Jam is like a protocol upgrade that is like approved to happen in Polkadot in the coming year or two, I would say, depending on the implementation. It does utilize Polka VM, but it's not. I wouldn't say they are like married together. Yeah, I mean, Jam happens to use Polka VM as its virtual machine of choice, but yeah, they are not. Jam would need a VM, and it chose the best one that is currently available, which happens to be Polka VM. I mean, the question is, if Polka VM a prerequisite for Jam? Yeah, I think we can answer yes. As in, Jam is assuming that Polka VM is fully developed and fully specified and completely production ready, and yes, that is the prerequisite. And Polka VM is already there actually. Like I think it's by and large fleshed out, and again we are deploying Polka VM not via Jam but directly to Polkadot by end of this year because we want to run smart contracts on it.
That's it from the participant side. The questions are done. Thank you so much for your insightful lecture, and thanks to everyone for participating and asking questions.
Yeah, thanks for the questions, and yeah, thank you also to the organizers. I hope everyone enjoys the rest of PPAX and learn a lot of things, and see you in the Polkadot ecosystem.
See you. Thank you. Bye.
Thank you.